Hey y'all, welcome back to another summary of a section from Rogawski's 4th edition calculus. And this time we're going to be talking about section 2.2, which is all about investigating limits. Within this section, we're going to answer in 15 minutes or under, hopefully. Sorry about breaking that promise last time. We're going to be answering what is a limit, when are they really defined versus when are they not defined, and questions of the sort. So let's dive in. Now let's start off with an intuitive example, that way we get the juices flowing. So I've graphed y equals sine of x divided by x. Now notice if I wanted to plug in 0, I would get sine of 0, which is 0, divided by 0. 0 over 0, that's what we're going to call an indeterminate form. So by plugging in the number, you don't get anything. However, what we can say is that the function kind of approaches something, right? Like, hey, if you were to fill in the dot, what y value would you give it? Well, it looks like we're tending towards 1 and kind of from either direction. This is what we mean by a limit. All we're doing with limits is we're saying, hey, based on points around, what y value do you think should go there at a given x value? So in this case, we would write the limit as x approaches 0 of our function, and we're talking about notation in a little bit. We'll get to this in a little bit. We would say that as we approach the x value of 0, our y value approaches 1. Let's go ahead and dive into this limit notation a little deeper. Now for some terminology. We say that the limit as x approaches c of a given function f of x equals L if, as you approach the x value c, it looks as though you approach the y value L. Now notice that we're talking about as we approach the x value c. We're not really talking about what happens at the x value c. So for instance, in the last example that you saw of the graph, it looked like we were approaching the y value of 1, even though at the given point we did not have a y value. There was a hole in the graph. So limits are mathematical guessing. It's based on points around where do you think you should fill in the dot. What y value do you think f of x should take on? Now I'd like to stress this point. Limits exist in a wide variety of contexts, but they are under no obligation to exist. You can have something that dives to infinity, you could have two functions that don't quite meet up, think of a piecewise function, and lastly you could have something that meets up, so that would be a situation where it exists. Let's go ahead and dive into a couple of examples so you can kind of see what we're talking about. Now that we have a basic idea of what limits are, let's try some. First and foremost, let's talk about this limit. The limit as x approaches -2 of, whatever the heck I'm calling this function f of x, because I'm real original. Well, as we hone in on the x value, -2, it looks like we're approaching the y value of +2. Notice that there's not even a point here, right? Like if I were to plug in -2 to the function, it would give me undefined. It'd give me 0 over 0 or something. But I'm not caring about that with limits. I only care about what happens around it and what it looks like it should be. It looks like we should have a y value of 2, if I were to make a guess. That's our limit. Now maybe a little bit trickier, how about this guy? The limit as x approaches 0 of our function. Well, in this case, we do have a spot. So hey, if I plugged in 0, I get y equals 3. But limits don't care about what happens at your point. They only care about what happens around it. Well, notice that if I go towards x equals 0 from the left-hand side, I'd fill in the dot at y equals 1. As I approach from the right-hand side, I'd fill in the dot at y equals 3. Which one is it? Turns out, limits have no obligation to exist. If you can't agree on a value, 3, 1, they're both saying different things, it turns out that's when we say that the limit does not exist. If there's no such value that you can agree on, we say that the limit does not exist. Now, what we could start to think about is, what if we just hone in on this side? Maybe we do get a limit here if we're just kind of ignoring that. And maybe we do get a limit here if we just kind of ignore this whole half. That's going to be one-sided limits. Now, as you saw in that last picture, we had some functions that didn't quite line up. But it still makes sense that we could do some predicting based on those pictures. For instance, if we were talking about coming up from the left-hand side, we would have reached a certain value. And if we were talking about coming up from the right-hand side, we would have reached a certain value. It just so happened that those values didn't agree. Kind of like the government, it turns out. So, this is why we're going to do one-sided limits. So, the limit as x approaches c from the right of my function, the little positive indicates from the right-hand side of our function equals L, if, as we approach the x value of c, using only numbers that are greater than c. We say right-hand limit because if you're a number line, the bigger numbers are to the right, and you're approaching this way. So, as you approach the x value of c from the right-hand side, we approach the y value of L. In a similar fashion, we say that the limit as x approaches c from the left-hand side, superscript negative, of a function equals L, if as we approach the x value of c from the left-hand side, so kind of walking up this way towards it, we approach the y value of L. Now, an interesting fact will be that you only have a full limit, meaning the limit as x approaches c without a superscript, if both of these guys agree. So, now that we've talked about one-sided limits, let's come back to this example real quick. If we do the limit from the right-hand side as we approach 0 of our function, that's only considering points to the right of 0. So I'm only allowed to walk up to x equals 0 from that hand side. Well, in that case, it's pretty clear. We approach the y value of 3. That's exactly what our right-handed limit is. Similar fashion, if we approach 0 from only the left-hand side, well, it looks like we approach the y value of 1. That's our left-hand limit. Now, just to throw in two more, if we approach negative 2 from the right-hand side, I would get a y value of 2. And if I approach it from the left-hand side, I also get a y value of 2. I mentioned it a little bit ago, but this is why we can say the full limit exists, because the limit from the left equals the limit from the right. This is why this limit does not exist, because the limit from the left does not equal the limit from the right-hand side. Here's an example for you. How about this function? What is the limit of my function as we approach 3? Well, it doesn't really settle on a y value. It kind of blows up to infinity in either direction. This is the idea behind infinite limits. Now, as you saw with the last graph, we can definitely have functions that blow up to infinity or blow up to negative infinity. I guess blow up in the opposite direction. Must be in Australia blowing up. Anyway, if we had a value where we blew up to infinity, we would say that the limit as x approaches c, where c is where the vertical asymptote happens at, of our function equals infinity. Similarly, if we had a value c that the function kind of goes down to negative infinity, we'd say the limit as x approaches c of f of x equals negative infinity. Now, the thing about this that we have to be careful of is that if I'm saying something like this, it means the function on both sides blows up to infinity. And if I'm saying something like this, it means the function on both sides goes down to negative infinity. More often than not, we have to use one-sided limits. As a quick example of that, consider the graph of f of x equals 1 over x. In this case, this graph is given by something kind of like this. Now notice as we approach 0, so in this case we'd be talking about 0 as our value c, from the left-hand side, we go towards y equals negative infinity. Therefore, we'd say that the limit as x approaches 0 from the left is negative infinity. And you can see a similar argument unfolding as we approach x equals 0 from the right-hand side, u equal infinity. Now, if I said something like, what is the limit as x approaches 0 of f of x, we would have to say it does not exist. And that's because we don't agree on an infinity that we reach. Remember, if you don't agree, you can't have a full limit without a superscript. That's how we're going to handle these infinite cases. As a quick example to end the day, let's consider the limit as x approaches 5 of the function 1 over x minus 5. Now, what we can always try to do, well, we could graph it first off, but an algebraic way of handling it would be to plug in your number and see if that works. And we'll get to more on why that is a good method later. If we were to plug in 5, notice that we get 1 divided by 0. Now that tells me you blow up to infinity, potentially in either direction. So really what it tells me is that this limit is undefined, that it does not exist. So if we want to be more specific and talk about infinite limits, this is where we need to go ahead and talk about the one-sided limits. How about as we approach 5 from the right-hand side? Now as we approach 5 from the right-hand side, that's going to be using numbers such as 5.1, 5.01, 5.001. So long as you're greater than 5, you can use it. So if I were to plug in those numbers, notice that 1, well, that just stays 1. But let's take 5.1. I'll have 5.1 minus 5. I get a positive number on bottom. And it turns out, so long as you're greater than 5, you'll always get a positive number on bottom. And since we have a positive number on top as well, we can say, well, positive divided by positive, that tells me I'm going to positive infinity. I'm going to infinity because the bottom is going to 0. I'm going to positive infinity because I have this relationship right here. Positive divided by positive remains positive. Now in a similar fashion, as we approach 5 from the left-hand side, notice that will be me using numbers less than 5. So like 4.9, 4.99, and you get the picture. If I plug those in, the common thing that's going to happen is that my bottom will be negative. Now, since the top remains positive, and the bottom is always negative as I approach 5 from the left-hand side, I'm going to be having a one-side limit of negative infinity. Yet again, I get the infinity because we're approaching 0 on bottom. I get the negative because we'll always have positive divided by negative, giving me a negative number. And as always, if you want to check, go ahead and check the graphs. But since these two do not line up, the best that I can say for this full limit right here is that it does not exist. One-sided limits tend to be a little bit more descriptive for us. But yeah, that's how we do this problem. Now so far we've only talked about limits as far as graphs go. And if you're doing something with a graph, you can always do it with an XY table, but I pledge to never do that again after 2.1. Here's a little bit of a hint for what's to come. If you're just given something like this, hey, evaluate the limit as x approaches 2 of x squared minus 2, turns out most of the time you can just try to plug in the number. What do I mean by that? Literally just try to plug in 2 to your function. 2 squared minus 2, that is 4 minus 2, so our answer is 2, and it turns out this is correct. Moreover, it turns out that if you're a continuous function, or if this is a point of continuity for your function, this will work every single time. So no need to graph this to figure this out, literally just plug it in. If this doesn't work, so in the case that you get 0 over 0, for now, what we're going to have to do is resort to a graph or a table. Hey y'all, thanks for watching that video on 2.2. Now, in summary, the whole idea is that you can figure out as you approach a certain x value what you think the y value should be at that given spot. That's the idea behind limits. It's just mathematical guessing. Now, next time, we're going to focus more heavily on the fact that you can do things without technically looking at the graph for nice enough functions. That's going to be the whole idea behind continuous functions, plugging in numbers, and how we handle things on the algebraic side. So until then, reach out to me if you have any questions, and we'll catch you all next time. Bye.